Okay, today we're going to start by looking at solving some simple inequalities, and then afterwards we're going to go on to compound inequalities. Alright, so let's just review some things that we should know or should have encountered before. There are certain inequality symbols. We have our less than, or greater than, right? And we also have our less than or equal to, and our greater than or equal to. Okay. All right, now before we even solve an inequality, let's just look at the properties of these inequalities. It is true, if we look at the following statement, 3 is less than, say, 8. This is a true statement. Now, let's ask the question, suppose I add 6 to each side. So if I add 6, then I would have 3 plus 6, and I'm asking the question, what happens to this statement? Would it still remain true? And the answer is, when they do 6 and 3, we get 9, 8 and 6, we have 14. It is still true that 9 is less than 14. So what we can say here is that the inequality did not change when we added. Right, so when we added a number or a term on either side, a positive number, there was no change in the inequality. If we took the same numbers again, 3 and 8, let's do a couple more things with them. So if we had 3 and 8, if we should subtract 6 from both sides, we'd have 3 minus 6, and we're asking the question, what's the sense of the inequality? So negative 3 and positive 2, all negative numbers are less than positive. So in both these cases, we can conclude that for addition and subtraction, the sense of the inequality remains the same. That is, it doesn't switch or turn on us. All right? Okay, so now let's look at multiplication and division. And some of you might remember this was what, if you were making any mistake, it was usually somewhere in this region. All right, so let's get some nicer numbers. Let's take some negative and positive numbers. So last thing I had here, no, I don't want to. Let's use negative 3, and since we just had it, let's use negative 3 is less than 2. All right, if I divide both sides by, say, 2, what do I get? I would end up with, minus 3 over 2, 2 over 2, and we're asking what is the sense of the inequality. So negative 1.5 would be the left-hand side, 1 is the right-hand side, and all negative numbers are less than positive numbers, so the sense of the inequality remains the same. Let's look at it. So that was division by positive 2. Let us take the same numbers, and if this time we multiply both sides by 2, we would have negative 3 times 2 And notice I'm putting in, I'm not sure what's going to happen, so I'm exploring. When I look at the left and right hand side as shown, we end up -6 and 4. So it must be true that the inequality did not change in these two cases. Right? So division and multiplication with a positive number did not change the sense of the inequality. Right, and I'm sure all of this is something that you have known already. All right, still using the same example of -3 is less than 2. Let's this time divide throughout by -2. So I would have -3 over -2, 2 over -2. We're questioning, let's put that in a different color since that's what I've been doing all along. -3 over -2, 2 over -2, and we're questioning what happens here. Simplifying each side, negative and negative will be a positive, so we end up positive 1.5 and -1 for the right hand side. All positive numbers are greater than -1. So here we see that there's a switch. There seems to be a reversal of the inequality. Right? Let's look again at if we should take the same inequality, -3, which is less than 2, which is a true statement. If we again now divide, we've divided already, so let's multiply both sides by -2. So I would have, anything I do to the right, I'll do to the left. And we're asking what happens to the inequality. When we multiply the left hand side, we get +6. Multiplying the right hand side, I get -4. All positive numbers are greater than a negative number. So again, we are seeing that reversal. Right? So if we look back at all the things that we've done, when we did addition and subtraction, there was no change. The sense of the inequality remained. That is, if it was a less than symbol, it remained a less than symbol, right? On the other hand, the only place that we got any reversal or changes was when we had multiplication and division of using a negative number. So multiplication / division using a negative number reverses the inequality. Right, so based on that little exploration, and you can try it for every number or so on that you wish, or every pair of numbers, we come up with certain rules. When dealing with inequalities, the rules are simple. One, essentially, we're going to solve the inequality exactly as we would an equation, except in two cases. Solve the inequality exactly as is done for an equation. And here let me write this except in big bold, except, not expect, except. And our first rule, of course, will be A. If we are multiplying or dividing by a negative number. Now, of course, we won't necessarily be looking at numbers, but how this translates is if I have minus 3x is less than 6. When I have to be aware that I'm going to be dividing by a negative number. So in doing that, you'll probably see me write this a bit, where I've recognized that I'm dividing by a negative, and hence I'm going to reverse the inequality. So I'll end up with the inequality x is greater than minus 2. Let's look at the second item or second thing. So we're solving an inequality just as I showed you that, exactly as you would do an equation, right? And I did, except that when I'm dividing by that negative number, I reverse the inequality. Let's put that in, reverse inequality. As you can see from the example that I gave here. And the second thing that we want to look at is if we think about this. If I have the number that 3 is less than 6, suppose I exchange the left and right hand sides. So that would mean I'd have 6 on the left, 3 on the right. How could I maintain the truthfulness of this statement? Well, I would have to exchange or reverse the inequality. So whenever we're switching the left and right hand side of an equation, of an inequality rather, right, we need to reverse. Switch. So switching left and right sides of an inequality reverses the sense of the inequality. All right, so let's even look at what would happen in an example in this case. So maybe I have done my work, or we had 3 is less than x plus 2, and as usual I would simplify by getting rid of the 2 here. So I might write 3 minus 2 just as I would with an equation, and so what I would end up is 1 is less than x. But in math, we want to be a bit more state our results in an active voice. Rather than saying 1 is less than x, I want to say what is x? X is greater than 1. So what I'd be looking at is switching the sides here, left and right hand sides would exchange, and I end up with x is greater than 1. Right? So these are the only 2 cases when we are solving inequalities that you really have to think about. If I'm multiplying or dividing by a negative number, watch out. Or if I'm switching my left and right hand side, again, I'll have to be careful. Alright? So let's look at some examples and practice what we've learned and go from there. Alright, so I'm gonna, now before we do some examples, let me talk about our set builder notation. And graphing. Alright, throughout this course we'll be using our set builder notation. So if you have gone through and solved So if we look back, we had solved, we were given, say, negative 3x is less than 6. We went through, and just to support the idea a bit more, I'm just rewriting this again. I'm putting a little r here to show that yes, I divided by a negative, so I'm going to reverse the inequality, and so x is greater than negative 2. So solving, that's my solution. My graph will be on a number line, and on a number line we'll indicate, it doesn't have to be perfect in terms of scaling and so on. We just want an idea of what's going on. So essentially I'm asking you to sketch your solution set rather than being absolutely perfect with it. Alright, so the number line, we see the labeling, it is x is the variable. We have x is greater than minus 2, so we'll put what's called an open circle here. Okay. So we have an open circle, and this open circle means that the number negative 2 is not a part of the solution, but the inequality now, if I'm looking at that inequality, it would be greater than, so it would be all that region above negative 2. So some of the solutions could have been, say, negative 1.99, right? Not the nicest number maybe to deal with, but if we even checked that in our solution, we'd have negative 1.99 is greater than negative 2. Some of you still have a hard time thinking in terms of negative numbers if you didn't have the number line present. So sometimes it might be easier when available to choose my x in a more convenient number to check. So if I put, if you'll notice, if I put the number, if I take a number that's in this region, say, let us check x equals 0 in my inequality. Negative 3 times 0 is less than 6. 0 is less than 6. That's a true statement, which is why 0 is in the shaded region. If I had taken something down here and checked, so suppose I said x is negative 3. If I put that in my original inequality, then what I end up with is positive 9 is less than 6. This is a false statement, which is why this region is unshaded. So the method of checking your solution, if you are working out an inequality, is to take a test point in the region that you have solved for and see if it still remains a true statement. Alright, so we know how to solve an inequality, we know how to graph it. It's an open circle if we have the strict inequality, that is the inequality whether we have greater than or less than. We'll soon look when we have what's called a closed circle. But before we go on, we also have what is called set builder notation. So we have set builder notation, which we have talked about before when we did set notation. And so in solving this inequality, I could say that this is the set of x's such that x is greater than minus 2. Typically, we are dealing with the real number system, so it's optional to put this in for most of our problems. But do pay attention to look to see, are you required to solve for x as a real number, or is it an integer, or so on. But our examples will take more of these into consideration. Alright, let's look at a second example. if we had, and I'll just do something simple. So example 2, x plus 5 is less than or equal to 7. Yes, I know we could probably solve this in our heads, but we have 7 minus 5, just the same way of solving or isolating the variable as we would in an equation. We end up with x is less than or equal to 2. My set builder notation or solution would be written as a set of x's such that x is less than or equal to 2. My graph would be 1, 2, 3. Right, this time, based on the inequality, since the equal sign is there, we will shade in the 2, the circle at the 2. This is called a closed circle. And a closed circle means that that item is included in the result. X is less than 2, less than or equal to 2, so it would be everything to the left of 2. We can again check our solution, so this would be the final thing, but it's always useful to do a quick check. So let's take a test value. I'm going to be very close to that. We call this sometimes the boundary. So I'm going to take things that's very close to the boundary, right? So the boundary is wherever I am putting my open or closed circle. Alright, so I'm going to take 2 test values, one that's actually in there and one that's not, to see if we will get a true statement and a false statement. So let's take a test value x equal to say 1.99 versus the test value x is equal to 2.01 or 2.1, doesn't matter. Alright, let's write back our original inequality. And what we're doing is we're putting these numbers, these test values. The first test value, which could be found somewhere over here, right? The second test value would be on this side. Okay, so we're just basically cutting it very close. So if I look at this, I get 6.99, and 6.99 is less than 7. This is true. So I'm happy that I've shaded the correct region. And now let's take the other side, which we know would be incorrect, but I just want to point out. And so taking the inequality, and 2.01, when we substitute plus 5, what's going on? This would be 7.01 and 7. This is greater than 7, so it's false. There is a change in the inequality. Or let me do this. 7.01, that is incorrect. It is not less than or equal to 7. Okay. Alright, so let's actually do some more some simple examples, but a bit more interesting. So let's look at number 3, and although it's simple, I want to solve it in 2 ways. Alright, so each time we get these, we want to not only solve, but we want to graph. Alright, so solve and graph. And of course, give your answer in set builder notation. There is another notation called interval notation, but we will not be using that in this class. Alright, the first way that I'm going to solve this is isolate the x, isolate the variable on the left side, as we would probably do in solving an equation. So I would have negative x is less than 7 minus 5 negative x is less than or equal to 2. And now we're going to divide both sides by negative 1. If it is negative, however, remember that you're going to have to reverse that inequality. So let's set it up. The way that I like to do it is not do everything at once. I'll just put a little r there to show that I'm going to reverse this. And I would end up x is greater than or equal to negative 2. This is my proposed solution. And of course I would graph. Remember to label your number line. And choose the appropriate open or closed circle. So here, because of the presence of my equal sign, it's a closed circle, and I will shade the appropriate region. The set builder notation or my solution would just be written as set of x's such that x is greater than or equal to -2. Because we're going to be working in real numbers mostly, I will drop the x as a member of the real set. Let's look at an alternative way of doing this. Alright, so we'll start out and we had what is given. 5 minus x is less than or equal to 7. Remember that addition or subtraction does not attract any change of your inequality. So I could literally, basically I'm adding, just to remind you from an equation point of view, I'm adding x to both sides. So I would end up with 5 is less than or equal to 7 plus x. Getting rid of the 7 now, I would subtract 7 from both sides. So this is what I'm really doing, as if I'm setting it up from an equation, or you could have just done the transposition. So I have 5 minus 7 is less than or equal to x, negative 2 less than or equal to x. Again, especially when we are ready to write anything in our set builder notation, we like to declare it as x, what's going on with x, especially in these simple cases. So switching the left and right hand side, recall that the inequality is reversed. Okay. When switching sides, the inequality is reversed. Okay. So we arrive at the same answer. Just be careful, keep those rules intact in your mind, and just use them, as I say, exactly how you solve an equation. Alright, now as we have done with equations, we can get a bit more sophisticated. That was number 3, so let's look at number 4. If you have your grouping symbols, your brackets, please remember it's the same method of using your distributive property. Get rid of those brackets, combine like terms. So if we start out here, I'm going to distribute, and I end up with 2x minus 6 plus x is less than or equal to 27. Okay. So as we did in solving equations, we are going to combine like terms on one side before we start moving anything around. So 3x minus 6 is less than or equal to 27. 3x is less than or equal to 27 plus 6. 27 plus 6 is 33. Oops. And solving for x, we're going to be dividing by a positive number, so no change to the inequality. we end up with x is less than or equal to 11, and so we would have our graph. You can change the scale of this if you wish. Oops. Alright, so let's make a, I don't feel like putting out 11, so we can have, say, -5 here, 0, 5, 10, 15. Alright, and we have x is less than or equal to 11, so that would be somewhere here. We can put in a closed circle, and we are shading everything below there. Remember to label your axes, and our solution set is x's such that x is less than or equal to 11. Some people feel a bit better about putting a pointer to say that this is the number 11. That's fine. Okay. Alright. Getting it even a bit more complicated. This is the last one that we're going to do for simple inequalities, however. Alright, so just to recap, anytime you have your grouping symbol, get rid of them, and then group like terms. Simplify each side before you move on. Okay, let's look at number 5. 7t minus 2 open bracket t minus 4 is greater than 6 minus 2 minus t. Alright, remember, during the class time, for those of you who are just watching us on video, in the class time there is a break, and we allow the students to write and do the problem. In video, if you're watching this on video, please pause each time that I write a question and attempt it, and then continue the video when you want to check your solution against mine. Right? That would probably be the most effective way. Alright, let's continue here. We would multiply throughout. So 7t minus 2t plus 8. Watch your signs as you go through, which is why I really put in a lot more negative signs than you probably are used to getting. So let's combine like terms on each side that we have. 5t plus 8, 4 plus t. Now we can do the transposition. Adding and subtraction doesn't change the sense of the inequality, so let's bring all the t's to one side. 4 minus 8 on the other, all the constants on the other. So we end up 4t is greater than -4, and hence divide throughout by a +4. No change again to my inequalities, and nothing strange happening here. Reduce, we end up with t is greater than -1. If I'm graphing, which for all my questions right now I will be asking for that, remember to put the appropriate variable on your axis. And here we have greater than, so if it's a greater than, it's an open circle. There's no equal sign. We are greater than, so everything beyond, to the right of that. Okay, now having done that, at this stage you can do mental checks or a quick check. If you were checking, it probably would be easiest, rather than say -0.99. It might be easiest to take that test value of say x equals 0 and substitute in your original inequality. 7 times 0, 2, 0 minus 4. Alright, it's easier to do as a mental check than what I'm doing here. which is actually physically writing it out, because you would have seen the first term went away, negative 2 times negative 4. This side would have given you positive 8. Is that greater than 6 minus 2? And 6 minus 2 is 4, so 8 is greater than 4. So you're getting a true statement on this half of the number line. Taking any other number, you on the other side would give you a false statement. So sometimes you do want to check, right? Especially when it's a longer inequality, or same thing applies when it's a longer equation. You might want to check your results rather than do it again. Again, writing my solution set. Remember the variable, please don't go in automatic mode and tell me everything is x. Anyway, so this is a set of t's such that t is greater than negative 1.